really basic physics that if we have an inductor and capacitor, so we will have resonating frequency equal to inverse of root of multiplying L and C. It works based on the copper electrons. If we have photons, microwave, or infrared, so the copper electrons will have enough energy to be separated, and by this way we will have different inductors. We have different inductors, so we will have different frequency and amplitude here. This picture shows a close view. You see that one of the advantages of MPs are working block multiplexing, and just by one single wire, coaxial SMA wire, you can have access to different range. This is the capacitor that here shown by C1, and this is the inductor that is here. So by changing the size of capacitor and the inductor, we can have different tunes, and we can detect different range of photons or microwave. The note here is that in electronic section, we cannot measure both phase and amplitude because it's real. And measuring amplitude is more easier than phase. Has information about the energy of photon and the number of photon and the arrival time. So first in electronic, we're trying to measure the amplitude, and if there is changes in amplitude, so we will switch the phase. The output signal of MPs is not too high, so it's around minus 60 dBm, minus 70 dBm, so we need to have a low noise amplifier that we already ordered from Caltech. So it amplifies the signal 36 dB. This is the radar system. I will not explain that much because I believe that Marjan will cover this slide. And this is the basic electronic circuit that we are going to work for kids. Actually, as you know, the making and designing this circuit maybe is time-consuming and also costly. Right now in market, we have a lot of companies, and there are lots of competition between companies that we can buy from them and develop the FPGA by ourselves. So the total into this circuits, we say SDR, software defined radio, because we have digitization and we can process our data in FPGA or computer. We are going to work in computer some parts, and we are going to process our data also in FPGA, Xilinx. In computer, we are going to work and have K10 from NVIDIA, the graphic GPU, graphical user interface. We try to have negotiation with different companies that they can they produce the SDR, and they are very famous companies in SDR, like for DSP, SPDwise. And recently also we are considering MicroTCA4 that DESI and other institutes are developing that. It's quite reliable and very fast. So maybe if we really are going to work on high pixels, the number of pixels is more than 2,000, so probably we will go to this. But right now, because we are going to just study how it is the signal of MP, because we don't have any idea about it. MP is just we read articles, but it's whether we have experience about that. So we are trying to start with this SDR. From different companies, as you see, the tools works well for us because it is included on our front end. And in our front end, there is a IQ mixer that we can reconstruct the signal, phase, and amplitude inside of FPGA. So it's also it's compatible with microsound because the IF frequency is around 20 to 80 megahertz, but the ADC is 200 megasamples per second. So the micros channel theorem also here is okay. And by that, we will trying to make signals to excite the MP frequencies. So here also we will have a kintex 7 that is 2 times more powerful than Virtex 6. So totally we have chosen to use ETUS as our electronic radar system. Here is our first plan and second plan for electronic radar system. First, we want to install MP. Probably it will be 2 months later because we ordered the project cables that we right now haven't. So first, we want to use sensitizer and VNA to detect that, and also we use some lights like red or blue, and we have fiber inside of the refrigerator, and we can check our inputs. And after studying MP's behavior, we are going to use ETUS. In ETUS, we have planned about FPGA that some of them will be done during these 2 months, and again, the rest of them remain them. We need to study MPs and make these lookup tables to be able to implement on FPGA. So it would be to plan for at least 8 months to 1 year. So we are going to have a good results from electronic setup. The other topic that I'm very big working on is FRBs, because many more FRBs are fast rate reverse. The difference between FRBs and pulsars are that pulsars are frequent. FRBs are not frequent, and their signal is stronger, maybe 10 or 100 times stronger and sharper, and also the deviation is probably the same at all steps. So based on the papers, the people trying to use FRBs for measuring the size of the universe, because they believe that FRBs are extragalactic, not intra. So if we have FRBs and we can measure this dispersion here, the dispersion is the time, arrival time, and total. It is the high frequency because when you have a signal and it passes through ionized intergalactic medium, so the high frequency will be arrived to us sooner, and the lower frequency will arrive to us later. So this dispersion, by measuring dispersion, we can measure the distance of galaxies, and by that way we can measure the size of the universe. We can probe dark energy equations, and also the probe intergalactic movements and baryons. So for first, I'm going to use FRBs, and we suppose that we have a lot of FRBs, and I will study about the different redshifts, how many FRBs we need to measure the fraction of baryons in intergalactic medium. It will be my plans for my job. Thank you.
First question is on MK. So what's the science driver? So you're doing all this hard work, all this effort, and then once everything works, what do you actually want? What science questions do you want to address?
Usually people use MPs for different applications. One of them can be observation. Astronomers are very interested to use them instead of CCD cameras because they have lower resolution, and also you can also find other applications in other areas like imaging, like chemical processing. What I like to do is that improving trying to work with MPs and trying to use that as a CCD camera. It would be one of the first step, and then we should see that.
Other questions?
A little bit more about the science side. It's okay. Shout. You said that you can use MPs for the observation, but which waveband? It's optical, it's regular.
Optical from microwave to the X-ray. We have different kind of MKits, depends on the fabrication. You can also have X-ray.
So what are you working on?
Right now we are working on microwave and optical. Yes. Microwave to the blue, the optical.
Did you show a picture of a focal plane? Pictures you showed, or do you have a picture of what the focal plane looks like? This is a single detector you're working with, I guess. Yeah. Yeah. Where do the photons go?
Oh, photons. Let me show you first. In experimentals, first, if you want to check it, we have some fiber cables here inside the refrigerator, and we can calibrate it, and we can put it our MKits first here, and we usually have a red or green or red blue for calibration. But I saw that in Palomar, I think that the Nazi group also put it there, and there is the same approach. They are trying to transfer the light inside the refrigerator by these fibers. And the MKit is backside of this aluminum. So if a photon hit the pixels, so we will have different, because all pixels have different tunes.
That's it. Right there.
Yes, yes. And this is the box that MKits will how do we borrow from ECL?
That's the backside.
Yeah, that it's inside of this aluminum sheet.
Oh.
But this is the same. This is 25, but we have here 20 pixels.
We cover the surface.
Yeah, we cover with aluminum.
Okay, this.
Well, maximum 2 centimeters to some meters. Depends on the number of pixels.
I mean this one.
This one is around. The detector only is around, I think, 2 centimeters, but the shield is coming from 4 centimeters.
I think Bruce has a question. You can unmute.
Sorry.
Oh, okay.
So is it not clear for me about the without system?
Yeah.
So what kind of without system system is optical or something?
So we have different kind of without system. We can use analog or digital, but recently people prefer to use digital. The scan would be like this, that Marjan will explain in details, that we will have our MKits. We ordered already our amplifier here inside of 3 Kelvin. We will amplify our signal, and we will have IQ mixer, and then we will digitize the system, and then we'll transfer to the FPGA. We'll do some process. No, it's for MKits. All MKits is sensor for opticals. But yeah, but for this, we could do 2 different scenarios. First, we design and fabricate all parts of the electronics by ourselves. That is time consuming. Then we have companies, so may expect to be quite from them. However, it was also a suggestion from Caltech, from Jonas, so we tried to choose Etrus because Etrus is complex. We have covers everything, and we can just focus on a feature. We don't need to waste time to design electronics by ourselves.
Bruce, do you want to ask? No? Okay. Okay, good. Let's thank the speaker again. So I'm going to move a little bit closer, see if that improves the sound. You're humming.
Not funny. Let's see how imagine comes.
Well, I know that one was boosted here. So
Let me tell this.
Hello?
Yeah.
My name is Marjan, and I'm the electrical engineer in this team. As Mehdi mentioned, I am working with a readout system of MKIDs. So let me start. First, let me share what we have done so far, our progress in ECL team. We have created this, since we're starting this lab from scratch, we have to purchase every single component, equipment, everything from scratch. So that was a significant amount of work done by every single ECL member who has contributed to buying the equipment and adding their contribution. Second, we successfully installed the ADR refrigerator, as you can see on the picture on the left side. It was we also went through training by an HPD company who came from Colorado. And third, we have carefully considered the design guidelines, and we selected a specific readout equipment, which Nancy mentioned was ANTUS detector. ANTUS equipment. So, and let me talk more about this readout system. So, MKID's device can be represented in this RLC circuit. So I'd like to show it to you. Yes. So each RLC circuit, and each of this RLC circuits is tuned to a slightly different resonance frequency. So the reason why MKIDs is so advantageous is that we can have only one hand amplifier and one cable to read out a multiplexed signal. So this signal is then sent to the room temperature electronic readout, and we have to send a probe of signals that has different frequencies, so that we can when the photon hits the MKIDs device, the resonance frequency changes, and that's how we can detect any kind of change happening in the MKIDs. When the photon hits, the surface impedance changes. So that's how we can read. And then column of sine waves is generated and sent through the system. And then we use FPGA to perform the readout system. So let me quickly go. What is an FPGA? FPGA is a field programmable gate array. It's basically, you can imagine it as a sea of many logic blocks and interconnects. And these logic blocks could be flip-flops, registers, clock storage elements, and in order to make a design out of it, we create lookup tables. So we implement those lookup tables on the FPGA. So this is how the FPGA looks like on that side. And this is how our software-defined radio looks like. Actually, let me show you another one. It's more clear. This one. So let me talk more in detail about our software defined radio. So here we have an MKIT device. We connect it to the hemp amplifier, and then this is all in the refrigerator, in the HR refrigerator, and then it's sent to, once it's amplified, this is a lower noise temperature amplifier, and then it's sent to the room temperature, which is here. There are some limiting factors, such as ADR, ADC, because based on the Nyquist theorem, we need to have a certain sampling rate, at least two times the other components, in order to get good data. So that's why we have to down convert it, because the ADC maximum in the market right now is 500 megahertz. That's why we need to down convert it here with an IQ mixer and an IQ. We use IQ mixer because it's basically a dual phase locking technique. And we have amplifier and attenuator. The reason why we have so many amplifiers and attenuators is so we could during the testing of the device, we pick some of the values we're getting, we could adjust them, and most of these amplifiers could be programmed to get a certain specific value. And then we digitize all this data, and then our digital data is sent through the signal processing unit, and then to the computer, and sent back to here. And then we can use the clock to synchronize this whole system, and it's all GPS locked. And I think that's about it. And we use, for this, like Mehdi said, we're not gonna design it from scratch because it's a couple of years to design it from scratch. So we decided to take advantage of the current available market options, and it just covers RF part of our electronic glass system. We have to add on top of it some attenuators and amplifiers. So this is how it just looks like, and this is its design. So there are different FPGA designs we could use. Then there's this one, digital down conversion, which is the FP450. And then we have to use channelizing design. So channelizing implementation in FPGA, and then FFT zoom, and then we have to do a buffer FIFO, and then hookup tables design, and then we can send it all to the computer and read it from there. Okay. Yes. Thank you very much. And this is all for the electronic system. And thank you so much for your attention. Please ask questions if you have.
table for?
Lookup table is so when you have a lot of logic gates, you can use each logic block to serve to have a certain purpose, and so lookup table is basically how you use those blocks. So just use certain output, and then if you, for example, if you have a multiplexer, and then you just select some of them and you have flip-flops, and so basically lookup table is how you implement the design. For example, if you want to have FFT, you could also perform.
I see, that's an example. Okay.
So low pass filter, you also filter.
Bruce, you had a question?
I thought the talk went very well. I have lots of questions that are just because I can't hear very well.
Oh, I'm sorry. I should have put the microphone closer.
So I just want to ask, the FPGA you've spoken of primarily for implementation of a lookup table, but isn't it also used to do fast FFTs?
Yes, absolutely. Yes, we could do FFT, low pass filtering, maybe more digital signal processing.
Thank you.
Other questions?
Very naive question. Programming logic blocks, there any programming, there means something physical happens inside that block, or it is all about the.
Yeah, okay. There is no naive question at all. It's a really good question, and we can think of, so if you'd like to think of logic design in like physically, it's a lot of transistors. So, you know, in logic it has certain outputs, zeros or ones. So, for example, AND gates, OR gates, NAND gates, they all consist of, they're all made up of different transistors, which physically, it turns on or off. Signal, there's a signal or no signal. So based on that, we can make design logics, so 0 or 1. And then, so that's what happens.
I can ask you later to completely understand what is going on there.
Okay, yeah. I would be happy to answer any questions.
Any other questions now? Thank you, John. Who's next? Yeah. Yeah, so please do keep the microphone close so that we're still here. And if you use the laser pointer, use it on the center screen.
So, good morning, everyone. My name is Aileen. I'm sorry. Good morning. Good morning, everyone. My name is Ainur, and I will continue describing our very challenging project that we started here at Netherlands University. And my part is, at this moment in particular, I will talk about the very specific task, which is tracing and arrays like automated telescopes. My idea is just to give an overview of how it will happen. So, what are the gamma ray bursts? They are, in a short, it's the extremely energetic explosions. They are the brightest events happening in the universe. Just a few facts. The first GRB is observed 50 years ago exactly, and its duration is the duration of GRBs can be different, varying between 12 milliseconds, the shortest one that was registered, and the longest one was over 7 hours. And the peak luminosity that was registered is 1.7 to 10 times to the power of 47 watts. And I have just tried to estimate it. I don't know how, it's not a professional estimation, but anyhow, it feels like you could light up 10 to the power 44 houses during 1 year. And there are still a lot of questions that we have. Scientifically, for example, we don't know what are the emission mechanisms of the GRBs, and what is the radius of emission and Lorentz factor. And so obtaining more data, making more measurements is, well, logically should lead us to more information, and hopefully we'll get hints to answers to these questions. So, how do we trace them? There is an agency, or I don't know how to say it, it's just one center, which is called GCN, Gamma Ray Burst Coordinate Network. And those guys, they obtain the information on the GRB and send to land-based and satellite-based, space-based observers. And depending on which protocol you use, it can happen in less than 1 second or a few seconds. And then the information is then observed. People, they can then resend the data, the analyzed data back to the center, which will be redistributed among all the observers. So the GCN claims that they don't have any human interaction, so it means that firstly, they send information very quickly, so all the people can immediately obtain the data. So, next. And on our side, we will be one of those observers around the world, and we plan to get 2 microscopes, one in the north part and one in the south part of Kazakhstan. And we will receive, as you have just seen in the system, we will receive the information from GCN, and we'll obtain the GRB location, and immediately by the remote control center, we will, the telescope will be redirected. And also we will take into account, of course, such factors as if the sky is clear, and if the weather is appropriate to make these observations. And what will help us to do this, there are a couple of devices, telescopes, and 2 EMCCD cameras, 1 IR cameras, and other different types of sensors. So that's to conclude. So GRBs are the brightest mysteries in the universe, and studying GRBs might open us the hints to what is the universe, and maybe we'll find out new understanding, and we will perform the tracing of GRBs by connecting to GCN, global worldwide network, and we will use automated telescopes, and one part will be to to work on the automation, and then I will contribute to reading out the data. So that is it. Thank you. And if you have any questions.
So specifically, what do you want to learn about the gamma ray bursts?
Specifically, we would like to understand the mechanisms of, as I have noted, mentioned in the beginning, the mechanisms of the bursts of the emission. And then secondly, we want to get the Lorentz factor, which means the coefficient of the proportionality of how the time mass changes in its moving, and then that's, I think, well, just to understand better, because at the moment we don't know much.
And is this system like many others in the world, or is there something unique that ECL is doing?
The uniqueness, as I see it, is in location, because I think we are the only observers in the central Asia part. That's how I would say.
There's something more important that's unique about these. So about the telescope properties and the camera properties.
I don't know how to answer your question.
The telescopes in the world have 3 cameras that can respond quickly to gamma ray bursts.
Okay. Yes.
Well, tell us to the whole audience.
Okay, so what we have very fast cameras, and there are only 3 in the world who can respond to so quickly respond and obtain the data.
So when you're presenting a science talk, always also say what are you doing that's special? What is special about this project? So again, these telescopes can point within 8 seconds anywhere on the sky, and the observations we had previously take about 60 seconds. So we're going to be seeing parts of the gamma ray bursts that haven't been seen before.
Mm-hmm.
And then also the fact that we're going to be observing 3 different wavelength bands. Most observations are just in one wavelength band, so they only get some very coarse information, whereas we'll be able to actually see is the spectrum rising, is it broken, is it falling, and so forth. So we're going to learn a lot of science because of these 2 unique technical capabilities, experimental capabilities.
Yes.
Other questions?
How big are the telescopes?
I can't answer the question because we haven't installed them yet, but we will in the next 3 months.
What was the model number of the telescope?
Yes, it's 700.
Right, so what's the 700 stand for? What does the 700 stand for?
I think it's wavelengths, I guess. No?
Aliyah will answer. Right.
70 centimeters.
Right,
Thank you.
700 millimeters, so 0.7 meter telescope. Question in the back.
So
Speak very loudly.
As far as I understand, satellites detect the gamma ray bursts, and they send the coordinates to telescopes in order to relocate, not relocate, reallocate the Earth telescopes to detect all of this. That is.
Yes, the detection of GRBs is done by the special kind of detectors. And the information is then sent, the location is detected by the GCN, Gamma Ray Burst Coordinate Center. So, and those people who don't have special kind of detectors to detect GRBs, we connect to GCN and obtain the location.
GCN is a supplement.
They get, I don't know, it's a center that is sending the GMP, and if you ask where they get the information, I think they have the detectors. On the image you can see XTE, where they get information from. They have a couple of satellites with the detectors that are especially directed to detect GRPs. Yes. But then there are other people, observers, who get the information from them.
So they detect them in the gamma rays and the X-rays, and then they send the location information, and then it's followed up, as she shows on the bottom, with optical telescopes, radio telescopes, high energy, trillion electron volt arrays, and so forth.
What about the satellite detectors? I mean, is it more efficient than base detectors?
Are the satellite detectors more efficient?
Yeah, I mean, let's see. Satellite detectors have the atmosphere barrier. I mean, so it's less probability to scatter. So gamma ray burst is very energetic burst.
Yes.
So it may scatter. I'm not expert in this field, but I think it may scatter the atmosphere, so we can lose some information or something like that. Isn't it?
Yes, we might lose some portion, but it's. I believe that satellite observation is far more expensive than the Earth-based one.
So it's financial problem.
I think it was having Earth-based observations since they are all around the world. Otherwise, people wouldn't use that. So I think it was having Earth-based.
So I want to add a few things.
Go ahead.
So I just wanted to add that Ainur has been working with us for about a day or two. That she has really had time to work on this. So she was very brave to make this presentation.
Thank you.
Because she's just started. But if you want to ask some more questions about gamma ray bursts, I would be happy to answer them at the break or the next opportunity.
Okay, good. And of course,
I could not understand the questions. So I can't hear you very well. Sorry.
okay. And of course, we should put on the ECL website summaries of the research and the basic ideas as well. All right, let's thank Ainur again. And move to the last of our ECL postdoc engineer talks. So while anything else getting set up, I'll quickly answer your question. So very fortunately, the Earth's atmosphere blocks gamma rays basically completely, or you would get fried. So you can only observe them from space. And yes, it would be great to point the Hubble telescope at a gamma ray burst every time we found one, but it takes forever to move, to point at a particular part of the sky. And it's, of course, its observations have been scheduled months in advance. You can't suddenly interrupt them and say, okay, here's a gamma ray burst, quickly go over and look at it, because people have been waiting for months to use the Hubble Space Telescope. So that's why you use a lot of ground-based observations. So it's not dollars only, it's just people want to use the best instruments for lots of things, and we can't always use them on the spur of the moment. Okay, good. Yes, definitely use the microphone. Go ahead.
Ready? Okay. So, hi everyone. So, I represent the theory and data analysis group at ECL. So I'm so far the only one theorist who's stuck here. And I'll be talking about the testing modified gravitational strength on cosmic structure growth. So this is not the only topic we covered. So we initiated different kinds of projects. And so far we got some results for talk about this project and many others we started. So let me start with the basic thing that everybody can understand. Oh, can you pointer? Just
the Chinese like and where it's small.
okay. So let me start with the basic thing. So we know that there was a Big Bang, and the universe was created and started expanding. At the same time, the Big Bang was hot enough to create particles, and these particles were, as the universe expanded, it was cooling down, and the structures formed in the universe. So, and there were two basic things that are basic things that are participated in the structure formation of the galaxies and cluster of galaxies. So we call them large-scale structure. So these are mainly the Hubble expansion, which prevented the structure from formation, and the gravity, which on the opposite attracted different parts of the matter, and then it turned into stars and all other structures. So as you see here, there is so the Hubble established the Hubble law, which is, told us that the galaxies are running away from each other, and also there are this Hubble formula is the Hubble rate with the rate of running how fast this galaxies run away from each other. So, and this is related to the Hubble rate is defined by the scale factor, which characterizes the size of the universe at which being passed, and it is related to the redshift. So, and we enumerate the different stages of the universe evolution by this redshift. So what we address in our projects is that are there different kinds of models. So it is to look at the structure formation and to find out which of the models is preferred. So, and there is a key thing in the structure formation is that the key is the gravitational stability. So if you have over-dense regions, then these over-dense regions attracts more matter, and if you have under-dense regions, then repulse. This under-dense region becomes less dense and less dense from time to time. As you know that also that the intent of the universe is that it composed of 70% of the dark energy, which and also the dark matter. So with ordinary UV and other things. So, and I think these three components are the main driving competing forces for structure formation. So, and so far we don't understand what are the initial conditions. And we only know that we suspect that these initial conditions, the seed the structures grow from, can be explained by quantum fluctuations. And these quantum fluctuations itself can be more complex object. For example, with the vacuum, if the quantum fluctuations represent some complicated vacuum, within this vacuum with more eternal structure. So let me start with a basic with some basic equation that governs the growth of structure. So this equation we use to study the growth of structure and look at different models. So what we do here is just we as you know, the gravity could be modified at earlier times or at later times during the evolution of the universe. And it's interesting to look at the structure and find out whether the gravitational constant, the Newton gravitational constant, changed during the universe evolution. So, and to do that, we proposed a very simple ansatz for modification of gravitational constant, which has peak location, the duration, the amplitude, and see whether by just computational methods find out and compare with just computational methods we can construct the observables and see whether with this compare these observables with the exact observations we are able to detect the modification of gravity at later times. So here the G is a growth factor, and these are two competing quantities of Hubble expansion flow and fraction due to gravity. Here you see the ratio of this amplitude to Gn and how it affects the growth rate and the growth function itself. So what we found in our work is that if you modify the gravitational strength at earlier times, then then you can introduce a very simple area law, telling that later today the deviation from the standard lambda CDM model is just the offset. And if you vary the parameters within certain small range, this the amplitude and the duration, so you can see that the deviation for small values of parameters is just exact constant, just exactly proportional, just reproducing this formula. So we also asked the question whether this early time modification method bring us the offset, so the later modifications work as the earlier time modifications. What we found out is that for late time modifications, so it seems it's different. So we tried power law, constant rising and falling. We found out that if you look at the deviation from the lambda CDM growth function, you see that at the end, when we observe it, when we will observe it today, we see that they are completely different. So even though, for example, you put some the same area, for example, if for example use the same area like under the modification curve, you end up with different kinds of offsets. And this means that, for example, in principle, if you look at the quantity which is sensitive to the modification of gravity, which is exclusion quantity, you could able to detect the different kinds of behavior, falling, constant, rising. So, but it turned out that even though we could detect some with 5% deviation, you can detect the deviations from the G Newton. So with using the data from the projected constraints or F sigma 8 measurements from the basic instrument. So we still could not distinguish the difference between the falling, rising, and different kinds of behavior. So and then our next project is just to, so we worked with some parameterizations. So we had some rising, falling monotonic behavior. The interesting question was whether we can approximate it with just 2 or 3 beans. For example, if you have modification, modified gravity strength, depending on the redshift. So you introduce some, you bin it into 3 or 4 or 5. So how good is the approximation if you approximate it with just bins without using the exact formula? And it turned out that by considering simple models, we found out that it's possible to approximate this kind of low falling, rising constant behavior by the beams. So we also looked at different kinds different kinds of models. So far, let me start. Let me just introduce you to some interesting behavior. So previously, we just modified gravitational G-Newton without telling you about the underlying theory. So here, so actually there are theories that can introduce modification of gravity on a theoretical level. So these are FR gravity, and this FR gravity acts like, so if, for example, FR is just one, then it's Einstein gravity. And if you use different kinds of power law or different kinds of functions for the power that is which tensor, so you can end up with different kinds of theories, and this different kinds of theory predict different kinds of behavior and effects on observables. So, what we tried is just a particular example. If you look at the, so FR gravity was motivated by that, you know, that the universe is expanding with its acceleration, and this FR gravity could introduce, like, replace this notion of lambda parameter introduced by Einstein. So you could just throw it away and introduce some more complicated functions and describe the effects of the observed acceleration as a modified gravity. There are also other models like TGP model proposed by Karachi. So this expresses the idea that the gravity is weakening, and it's weakening because it's it leaks into the fifth dimension. So, and based on this model, you can derive the Hubble constant, Hubble rate, and then use this Hubble rate to solve the growth equation. And here you end up with this kind of, if you compare the effect of TGP on the growth of the L sigma in quantity, we can approximate it with just means up to 1%. So then, when you get different kinds of models, you can just forget about different kinds of functions and introduce binning. And if you analyze the data, you can just bin just look up the measurements of particular Z's and introduce these bin parameters. So what we did this week, for example, we tried to test the idea of Armand as a guest, you know, here. So we look at the phenomenon of strong lengthening and use it to look to test whether we can extract or tell anything about whether the universe is flat or not, just from the measurements of the time delay distances to for the time delay distances, time delays for the images of strongly lengthened stars like supernova explosions and other objects. So here the idea was that if you look at the quantity here, and if you do, introduce the difference between the time delay distance presumably in curved space and the relation that describes this dt the difference that zero curvature, assuming zero curvature, then you find out that this difference is actually proportional to the curvature parameter. And in principle, if you put if your measurements are precise, you can detect this curvature parameter. And we look there are assumptions that if you have some uncertainties on the moving distances from to the star, from the observer to the star, and also from the observer to the lensing system. So, so we put quantities with quantities and also the uncertainty, the expected uncertainty on the measuring these time delay distances. We found out that if you want to detect curvature, then you have to significantly reduce the uncertainties for that. This is to stars, and this is to the source and lens. So in principle, if you reduce the uncertainties of the distance, of the measurements of distances, you could make constraints on curvature parameter. So maybe to 0.005. So and then in principle, this if this thing is done only on a single system, and if you use many more systems and data sets, probably you could detect the curvature parameter even more precisely. So, we also work, significant time was spent also on using AFT cam to look at the primordial gravitational wave speed effects of the B-mode parameterization of CMB. We also worked for some period of time with students, and one of the students sitting here. And also when I just started with ECL, we initiated a project on time delay estimation with machine learning and GB processors. So thank you for your attention. So this is all.
Questions?
Does the DGP, I think you said it predicts that G is falling?
Yeah, it's falling.
And by how much does it fall?
How much in percentages from Geneva?
Yeah,
By 30%.
by 30%. So
It's really huge.
okay.
It's really huge. The most simple behavior we tested was just the 5%. And DGP was just among the least of things we tested.
Yeah.
Just curious.
So it's 70% now of what it was originally.
Yeah.
And were you able to distinguish? Are you able to distinguish that amount of falling?
Well, yeah, in principle, for example, if you beam potential, I mean, the G in Newton behavior beams, you can, in principle, so if your measurements, so the beaming procedure is accurate up to 1%.
Okay.
And the measurements from, for example, the projected measurements of sigma average quantity is 2-3%. So in principle, it is sufficient to be detected.
Okay. Right, thanks.
Any other questions? Let's thank you again. And Mr. Caldwell is giving the first of his lectures, science lecture on gravitational waves and inflation. And
You want to
you
take
want to
a
use
break?
your laptop?
Yeah, while I say something.
Who is Bruce, are you staying on or are you off? Well, so then. Okay. All right, then I'll use the microphone. Oh, that HDMI cable. Question is, all right, give it a whirl and let's see. Oh, yeah, we have to show this next. Okay. Okay. Professor Caldwell is professor at Dartmouth College in New Hampshire, United States. He's here all this week. He's a theoretical physicist who's worked on a wide variety of topics. He's spent time at Princeton University, University of Chicago. Where am I leaving out? He's been a frequent visitor to Caltech, and he's actually spending this semester on sabbatical at University of California, Berkeley. So it's very nice to have him there. And I'll just sort of get right into his talk.
Great, thanks. Thank you, Eric. Thanks for having me here. I have a long but interesting story to tell you about cosmology, and this, my title is a unique and observable imprint of inflation. And since I'm so far from home, I'd like to show a few pictures first, so you can know where I'm coming from, what I think about, or what I look at every day. So this is a picture of what the countryside looks like near my house, near Dartmouth College. And I like looking at the sky. It's the same everywhere, actually, but sometimes the clouds are a little different. Anyway, and staring at the sky is what we're actually all interested in, because that's where all the cosmological information is coming from. Okay, so to tell you where New Hampshire is, I have this little animation. Great. It works. All right, excellent. Okay, so yeah, so I have this little towers of 10 frames. Usually I go forward, and everyone knows that we're starting on Earth, and then we go forward to larger and larger scales, getting up to the size of the observable universe, thousands of megaparsecs in radius. But here I'm interested in just the very first frame, because this is the map of the Earth above where I live in New Hampshire. Okay, so this is what it looks like. The star is approximately the location of New Hampshire in the northeast corner of the United States. We're halfway between New York City and Montreal, Canada. And this is what it looks like, presumably right now. I can't be sure. Anyway, this is part of the college. And you can see the countryside surrounding it. There are hills and trees. This is the physics building right here. You can tell because it has the astronomy domes on top of it. And these other buildings are chemistry and earth science, and that's a dormitory right there. So to give you an idea what the experience is like for students at Dartmouth. Okay, so this is where I usually work, and that's where I look up at the sky and have questions about where did it all come from. And so to try and answer some of those questions, I'm going to tell you this interesting story that connects a lot of different types of physics, and hopefully I'll be able to explain it in pretty basic and easily understood terms. So we have our information about cosmology from the cosmic microwave background. This is one of the beautiful maps from the Planck satellite, and you all know that this is, if you've seen this before, that this is the fake sky, because this is the artistic interpretation of the sky, because there's no galaxy in the middle of it. It's okay. But nevertheless, this is a beautiful picture showing the temperature variations across a broad range of angular scales. And by measuring that, how the temperature pattern varies on large scales to small angular scales, we gain some information about the initial pattern of density perturbations in the universe and how they vary with scale. Okay, and that gives us some insight into where all these fluctuations came from originally. Okay, and then shifting to a different map produced by the Planck satellite, we have the high frequency 353 gigahertz map, which is dominated by dust in the local universe. But this map is interesting because of all the swirly lines that you can see here. It almost looks like a Van Gogh painting. All the swirly lines, and those are the that's supposed to represent the polarization. It's a way of representing the polarization of light from the orientation of these lines, the orientation of the dividing field. Okay, and we're really interested in understanding if there's a primordial component to this polarization signal, because that primordial signal can tell us something about the origin of the universe. That's what I'm most interested in. And I think making that measurement is one of the prizes right now in cosmology. And the reason it's a prize is because there's a unique and observable imprint of inflation of the early history of the universe. It's not necessarily there, but it could be in that pattern of swirls. And what I'm going to tell you about today is partly that story about inflation, but also about a model, a version of this model of inflation that I've been working on that makes an additional unique and observable prediction. Okay, so what are we looking for? In looking at that pattern of the swirls in the map of the cosmic microwave background and polarization, we're looking for these sort of atomic imprints, these left circular and right circular swirls. These lines are supposed to represent the polarization of the light, the orientation of the electric field on the sky, and we want to see if there are coherent swirls. Now, there already have been seen coherent gradient patterns like this on the sky. And those are nicknamed E-mode polarization, E for electric, because electric fields are produced by gradients. And then there's the B-mode, probably familiar with, produced by a curl, a swirl, that has a non-zero vorticity. So that's why they're nicknamed E-modes. And you know that you can see E-mode patterns in your everyday life. If you walk outside on a clear day when you can see the blue sky, like I was describing, and you polarize sunglasses on, you can see E-mode like this. Not this one, but this one, because it's surrounding the sun. It's actually, there's a radius such that if you look 90 degrees away from the sun, you see the E-mode pattern circling the sun. Okay. Go on and measure that yourself. The sun is a pretty bright source, first astronomical object discovered other than the Earth, so that should be pretty easy. So that's what we're looking for, swirls in the pattern of C and B. They're coherent on degree scales with sub-microkelvin magnitude, and we can also ask if there's a preferred handedness to these swirls. Should they be detected on the sky? Okay. There was a false alarm a couple of years ago It was thought that maybe these swirls were detected. This is the map produced by the BICEP experiment. The little line showed the orientation of the electric field, and if you squint, you can see where these swirls might be. Around here, you can see plenty of swirls. Unfortunately, it turned out that you cannot make the case that these are primordial. The most likely explanation for the swirl patterns that they saw were from dust magnetic fields in the foreground universe, which they discovered when making a more careful comparison with the map produced by the Planck satellite team. So not so fast, the search continues. Okay, so now I want to spend some time telling you about inflation, reminding you of inflation. So here's my timeline of the universe, provided to me by the European Space Agency. They produced these beautiful graphics. We have the beginning of the universe to the present day universe, and it almost looks like a slice from a biological sample. It's like the universality of phenomena. Okay, so I'm going to be talking about inflation, the accelerated expansion of the early universe. It's a theory proposed to explain the origin of large-scale structure and also to solve a number of cosmological problems, get rid of unwanted relics, solve the horizon problem, and essentially give the universe a clean slate to start from. Why would the universe need a clean slate? That's an interesting story. I think we can go into that later, but let's proceed with inflation here. So, what is inflation? It's a brief period of accelerated expansion in the early universe, and it puts the bang in the Big Bang. So, in order to talk about some of the details that I want to present, let's start with the basics about inflation. Inflation is the physics of a cosmic scalar field, not unlike the Higgs, which is a cosmic scalar field that pervades the universe with the same vacuum expectation value everywhere, because we know that all particles have the same masses everywhere in the universe. So the idea is that there's another field beyond the Higgs, the inflaton, that pervades the universe. It's homogeneous and isotropic. And nowadays we can't feel it, but in the early universe it played a very important role in shaping the evolution of the universe. So the physics of inflation is the physics of a cosmic scalar field. The equation of motion for a scalar field is given right here, and h is the Hubble constant, v is the potential energy density of the scalar field, and the equations of motion resemble that of a particle rolling down a hill with some friction caused by the expansion of the universe. Inflation occurs when this inflaton is the dominant source of energy in the universe, and when this inflaton rolls very slowly down the potential. Mathematically, this corresponds to the slope of the potential has to be sufficiently small so that it doesn't roll very quickly. And you can show easily from that condition that results in the Hubble constant being approximately constant. You can solve that for the rate of time of change of the scale factor, and you find that it grows exponentially. And that's inflation. When the scale factor, the size of the universe, grows exponentially in a short amount of time. So for a realistic value of the Hubble constant on the order of 10 to the 14 GeV, in just a jiffy, it grows by many orders of magnitude. And these are canonical values, 10 to the 14 GeV, and growth of at least 60 eFolds. Okay, so there's something else that happens that's really interesting. The scalar field, as it rolls down, it can also fluctuate. And that's one of the most fascinating things about inflation. Sure, there's this rapid exponential growth, but it would all be for naught if there weren't little fluctuations in the scalar field as it rolls down. And the fluctuations in the scalar field can be understood in terms of quantum mechanics pretty easily. If you consider, by analogy, the quantum mechanics of a pendulum. experiment. If I had a pendulum in my hand right here, swinging it to classical pendulum is fun, but it's totally boring because we all know how to solve the equations of motion of a pendulum. Sine theta. Okay. Square root g over L. Okay, but the quantum mechanics of a pendulum is very interesting. We have a pendulum at some initial time ti with a length li, and we have it perfectly at rest and let out the rope very slowly. Then there's no change in the motion of the pendulum. It just sits there. So from initial to final, there's no change. But quantum mechanically, there's a huge change because there's an irreducible bit of energy, the 0-point energy, the 1 half h bar omega, can't go away. And if we let out the rope quickly, we find that our pendulum is now in an excited state, and we've created a huge number of quanta. Letting out this length of rope is caused by, in the analogy, the change in the length of the rope is caused by the rapid expansion of the universe. And so there's an exponential number of quanta that are created of this pendulum. And this can be applied to the description of fluctuations in the scalar field that drives inflation itself, and also in fluctuations in the space-time metric itself, leading to gravitational waves. Okay, so equations of physics of a cosmic scalar field. What's really interesting is that there are quantum fluctuations of the scalar field with an RMS amplitude. They go like the whole constant divided by 2 product quantity squared. That can be translated into a density spectrum, and that can be applied to describe the origin of a gravitational wave spectrum. And this is the most exciting news here, the origin of a spectrum of long wavelength gravitational waves. So I've got various factors to sum up the polarization states, plus and cross, and for each wave number, the RMS amplitude goes according to this formula. Now, there are 2 more details I have to tell you about for inflation. One is that the Hubble constant is not exactly constant during inflation, but it decays slowly. So the result is that this RMS amplitude gets slightly smaller with time, and that's characterized in terms of a spectral tilt incidence, S, which describes the power and fluctuations of a given wave number. And since h decreases slowly with time, and that power decreases slowly with time, and we characterize that by a value of this tilt that is less than 1. The second thing is that the amplitude of the gravitational waves in the density spectrum has a very nice value of this amplitude. The ratio of the gravitational waves to the density perturbations is 16 times epsilon. It's an amount that we can predict in a particular model of inflation. This epsilon is a slow roll parameter. It has to be much less than 1. And so this ratio is much less than 1 times 16. So the prize of cosmology is to detect the long wavelength gravitational waves, which I've attempted to describe where they come from. And these long wavelength gravitational waves are a unique feature of inflation. There's been no theory proposed that can explain where they would come from otherwise. And they may be the imprint on the cosmic microwave background in the form of these EMOs. So inflation, what does it do? It takes these quantum mechanical fluctuations and waves and stretches them to outside the horizon. So we show scale versus time. This is illustrating the horizon radius during inflation, nearly constant. And then it begins to grow as the universe expands after inflation. And the dashed line shows a particular wavelength. As it gets redshifted with time, it passes outside the horizon and then re-enters inside the horizon. No other process can do this, to produce take small fluctuations, stretch them to beyond the horizon, and then allow them to re-enter. So if we see very long wavelength fluctuations, they must have come from inflation or something else. But this is the best explanation we have so far. Okay. And then those long wavelength fluctuations imprint on the cosmic microwave background. This is a little picture. If I had a whiteboard, I would draw this, but instead I spent a few minutes and drew this on the, so I drew it on the PowerPoint. So here's us at the center of the universe. Right? We're entitled to that. Right? Okay, and this is the surface of mass scattering. When the universe became transparent to electromagnetic radiation, that's the instant of mass scatter, and photons scatter off of electrons and move along the line of sight to us. We see them, and we can measure their polarization, and it's the subtle interplay between these photons and either the density perturbations that produces the E-mode polarization, or these photons with the gravitational waves, which squeeze and stretch space-time at the point of scattering that leads to the B-mode polarization. Okay, so to remind you again, this is what we're looking for. This is the CMB as viewed by the WMAP satellite. These white lines show the polarization that they measured. They were unable to determine if there was E-mode polarization, but this nice picture gives you an idea of what you should be looking for these swirls. Again, these are unique and possibly observable imprint of inflation. Okay, let me just point out that there's a couple of problems with inflation, because that'll help me justify introducing my subsequent theory. You always have to do this, explain why those who preceded you were missing something. Okay, so slow roll for a scalar field for a potential, the simplest potential you can imagine writing down of a massive scalar field implies that the mass has to be much greater than the Planck scale. That seems to be a problem, or it could be a problem if we want to control the mass against quantum corrections. The classical theory of a scalar field would be inadequate to describe its evolution if its mass really were much greater than the Planck mass. Likewise, a detectable gravitational wave spectrum implies that during inflation, the field actually rolls quite far down its potential. It rolls a distance that's much greater than the Planck mass. And that's also a potential problem for models of inflation, for the theoretical consistency of the scenario. Okay, with that in mind, I'm going to tell you about a variation on inflation that I've been working on that predicts an observable spectrum of gravitational waves and makes a couple other predictions too. Okay, so what's different here is now I'm going to describe a model of inflation that has an inflaton, a scalar field, but also has a Yang-Mills field. So Yang-Mills is a non-abelian generalization of electromagnetism. The Lagrangian can be written down. There's some general relativity, and here's the Lagrangian for the Yang-Mills. A is a vector potential, just like any EM, and it's a cosmological field. So that means I want it to be homogeneous and isotropic, just like the cosmic scalar field. So this is a leap. You have to accept that I'm going to have a constant gauge field. That is, I have a multi-component vector field A. The subscript I is the space-time index for x, y, and z directions, and the superscript A is the SU2 flavor index. And I'm going to take the ansatz that it's homogeneous and isotropic. This leads to some really fascinating physics. The physics of a cosmic gauge field is very different from the physics of a cosmic scalar field. It fills the universe with homogeneous energy. And just like in optics, there can be, like in a dielectric, there are light can propagate, there are other modes that can propagate through it. It supports density perturbations, of course, but it also supports something, something in addition to gravitational waves. It supports waves in the gauge field that couple to gravitational waves. And the waves that couple to the gravitational waves have a handedness to them, which is really strange. So, in optics, there are things called birefringent materials or diprobe materials. This is an analogy to a diprobe material. Okay, I have a little animation to get you in the right frame of mind. Have you ever played with one of these? It's a top, and it likes to spin in just one direction. So it likes to spin in that direction, but when I spin it the other way, it resists. So it's a top that has a handedness to it. It likes to spin in one direction and not the other. But when you try to spin it in the opposite direction, there's an instability. Actually, there's a series of instabilities that ensue that force it to rotate in its preferred direction. So the Yang-Mills field is sort of like that top. It has a preferred direction that it would rather rotate. Gravitational waves propagate with a different dispersion relation through this material, depending on whether they're right circularly polarized or left circularly polarized. So that's like that handedness. And there's an instability that can be exploited to amplify one handedness of the gravitational waves over the other. And that's the instability that I'll be taking advantage of in this model of inflation. Okay, so here I am dreaming and looking up at the sky. This model that I'm going to be describing to you is based on some work by previous groups, as at Wyndham, at Sheikh Jabari, and Irani Loso, that went into the name of pro-natural inflation. The idea is that you have a scalar field like an axion particle, I'll call it chi, with some potential v, and it's in the presence of this cosmic gauge field, and there's an axion-like coupling between the inflaton or axion and the gauge field, the term Simon's term. And we have a standard axion type potential, which you can simply replace by m squared chi squared. This is a really clever model. My hat really goes off to the people who thought this model up, because it does some really, really nice things. First of all the masses are much smaller than the Planck scale. So it solves that problem of needing to have super Planckian masses. The coupling, the Yang-Mills coupling is small. It's on the order of 10 to the minus 3. So that's a reasonable value. Quantum mechanically is a very reasonable theory. Then it does something interesting. It produces a spectrum of gravitational waves that are chiral. That is, there's an imbalance between the left circular polarization and the right circular polarization. And the handedness matches the handedness that's built into the Yang-Mills. And it exploits an instability and amplifies one of those hands over the other. Unfortunately, this model was too efficient at producing gravitational waves, and the fact that we haven't observed any yet can be used to rule this model out. So this is the current state of affairs, measurements of the attention to scalar ratio R versus the spectral tilt of inflation. These are the likelihood contours determined by Planck and the Bicep-Planck experiment for joint analysis. Basically, your theory of inflation has to lie somewhere in here. The chrononatural inflation that I described predicts a point that lies somewhere way out to the left-hand side of the box. And for reference, although this is the current state of the art in current experiments, the CMB stage 3 experiments should be able to measure at 3 sigma a 10 to the scalar ratio of 2 times 10 to the minus 2. So they should be able to measure anything above this line at 3 sigma. Okay, so the original model of chrononatural inflation didn't work, unfortunately. So what we've done is simply change the potential. We just lowered the power law index of the potential to some value n. Instead of n being 2, we made it a fraction. So the fraction has to be bigger than 0, but small. Okay, why did we pick that? Well, the motivation comes from looking at this plane. The original m squared phi squared inflationary model, basically chrononatural inflation without the gauge field, predicts too much gravitational wave. And you would expect it to produce something up here. It remaps that location far to the upper left. So we picked a potential that would naively predict gravitational waves lower to the right. The gauge field will put us, hopefully, somewhere where we can see the gravitational waves. Okay, so I conspired to pick a potential that would give me an observable amount of gravitational waves. Okay, so turning on the gauge field does something really beautiful. The potential itself is far too steep to inflate on its own, but for a wide range of initial conditions, the coupling flattens the effective potential. So the scalar field doesn't see just B, but it sees B minus pi over n FF dual as its potential. And there turns out to be an attractor behavior, which that is essentially flat in the pi direction. So it's very easy to inflate without finely tuning the potential. Some technical details about the calculation. It's much more complicated than standard inflation. In standard inflation, there's just one node in the scalar sector for fluctuations. Here we have three dynamical modes and 3 constraints. So the Hilbert space of quantum fluctuations is bigger by a factor of 3. And for the tensor modes, there are actually 4 dynamical modes instead of just a single one. Why are there 4? That's because there's, for each polarization, left, right, of the gravitational field, there are left and right fluctuations in the gauge field. So that makes 4.
They're all transverse.
They're all transverse, yeah. Okay, and so with our model, this is what we predict. Depending on the value of n that I choose, you'll lie along one of these curves. And I picked a spot here in just one of the models where that little n is it's a small index for the shape of the potential, but it is far too steep to inflate on its own, so it needs the gauge field. And I picked this point because it's going to be interesting. It's within the 2 sigma, it's within the 1 sigma region of the constraints here. And so it's produces a viable amplitude of density perturbations and tensor modes. Okay, and it conceivably could be observed in the next few years by stage 3 CB experiments.
So, was it dash lines?
Those are just 3 different families, 3 different choices of n, the power law of the scalar field potential.
So if, for example, if you become like that one, then you can say that the other one can be.
Yeah, That's right. I investigated 3 different models, essentially. And what changes as I go up and down? The annulus coupling and the mass that I'm free to adjust. But due to the constraints, I only have a single parameter, effectively a single parameter that moves me up and down on that curve. Okay, so I have a model of inflation that I'm describing to you that predicts a potentially observable amplitude of E modes. That's good news. When I told all my CB experimental friends, they're really excited because experiments that are stage 3, so this is something that they could detect. Now, there's something extra that this model predicts that's pretty exciting. Actually, there are 2 things that are really exciting. It predicts that there's an asymmetry in the left and right circular polarizations of the gravitational waves. And so, in fact, it predicts that 90% of the energy in the gravitational waves are, for the sake of argument, we'll say left-handed rather than right-handed. So the chirality parameter is 0.9. So let's just say it's 100% left circular polarized. There's something else you can try and look for, and that is there should be a correlation between the temperature pattern and the B modes. Correlation between the E modes and the B modes that should be 0 if there was a balance between left and right circular polarizations. This is fantastic. This is something that should not be there in a normal case, but this model predicts uniquely.
Okay, result is some lead to the E modes?
No. This is there are other scenarios that predict EB or TB, and it's through a lead from E to B. It's intrinsic from the very beginning. That's when the polarization is formed. That the E and B mechanisms are correlated. So what this means is you should go look for the curl pattern in the polarization. You see it on large angular scales, and you spot gravitational waves. Congratulations. But you should check for something else also. Is the curl pattern correlated with hot or cold spots? Is it correlated with the gradient pattern in the polarization? If the answer is no, then the gravitational waves have no preferred amplitudes. This model predicts that the answer should be yes, the gravitational waves do have a preferred amplitudes. Okay, so that's something unique to look for. Now, as long as there's a handedness, then there's an opportunity to do something really exciting, and that is to explain the matter-antimatter asymmetry of the universe. This is something no other model of inflation attempts to do. And this, at least in this toy model, actually is able to do it. Okay, so there's an asymmetry in antimatter in the universe, in that there is basically no antimatter in the universe, and we characterize this degree of asymmetry by the ratio of baryons that we observe today to the photons that we see today. So the baryon to photon ratio is something we like to be able to predict. Well, I can predict with this model the ratio of leptons to photons, and then I can invoke some standard model physics to convert leptons into baryons and produce a model of baryogenesis through leptogenesis. And it starts with the gravitational waves. The gravitational waves can be converted into a lepton asymmetry. So let me explain. During inflation, predominantly left-handed gravitational waves or right-handed gravitational waves, we biased space-time to have a handedness, to have a texture. Now, normally, in an expanding universe, when there's particle creation, there's no fermion creation. And that's because fermions have a handedness. And I think of it physically as them not fitting into the space-time. There's nothing that breaks the ambiguity of left-handed or right-handed, so why would you produce any fermions? But in this case, that bias favors the production of left-handed fermions over right-handed fermions. And there's a result that encapsulates this. It's the gravitational anomaly, which has a Feynman diagram that looks like this, where the squiggly lines are the gravitational waves. The triangle here are some neutrinos running around, and then the dashed line coming out is the axial current. It's a current that tells you the number of right-handed minus the number of left-handed particles. And it's produced by this volume integral of R dual to curvature, which is only non-zero when there's a difference between left and right-handed gravitational waves. Okay, so to put this all together, you can evaluate this integral and predict the number density of leptons and convert that into the ratio that we're trying to observe, the lepton to photon ratio. I should have said that there are some requirements for any successful baryogenesis scenario that were laid down by Sakharov, called Sakharov's conditions. Basically, you divide the baryon number, which we do by the lepton number. You have to have CP binding, which we do because the photon gauge field are very odd due to the FF coupling. And the process has to be out of equilibrium, and inflation is definitely out of equilibrium. So all three of Sakharov's conditions are satisfied. Okay, and here's the exciting graph. Get excited about this because this model of inflation predicts the baryon to photon ratio, eta, to be 6.1 times 10 to the minus 10. That's the observed baryon to photon ratio. In this scenario that do that lie along this dashed line. So I've actually just taken, for those three families that I investigated, I actually investigated 4 or 5. I didn't show them all. I found the point at which they produce eta matching the observable value and then connected the lines. So I have a prediction of models of inflation with an observationally viable spectral density and tensor to scalar ratio R. Explain the matter-antimatter asymmetry in the universe should lie along this dashed line. And this dashed line is above the CBS3 line. So in the next few years, it should be testable. This is the 3 sigma sensitivity curve. So it should be detectable. Not only that, this dashed line is a lower bound. Anything that I can think of to change the scenario, change the particle content of the standard model, temperature, will only cause this dashed line to move up. So this solves a problem of motivations for inflationary experimentalists, in which many inflationary models predict gravitational waves, but at an amplitude that's below the screen. This predicts gravitational waves that are observationally detectable and has a lower bound. So it won't be like some elusive Tantalus object that's always out of reach. So this is observable. Okay, so that's the model. That's my long story about inflation, about this model of axion gauge field inflation. It makes several observationally predictable, observationally testable predictions, a viable scalar spectrum, an observable tensor spectrum, a unique imprint in the C and B in the form of the B modes, and then the asymmetry, the chiral asymmetry, predicts that there should be new correlations that would otherwise be zero that you can look for, the TB and the EB correlations. And then this also matches up and explains the matter-antimatter asymmetry of the universe through a model of abiogenesis, and that implies a lower bound for the B modes. This model will be be tested within the next few years. And that's my story.
So, if we find some features in the primordial spectrum,
Yeah.
so do you think from the naturalness point of view, this can be considered, for example,